So in theory, if I press this, it's going to move it on. Is it? Which one am I pressing next? Yeah, okay. Put that down. So a bit of my background, I did an undergraduate, integrated master's computer science degree, went on to study a GPUE PhD looking at improving the performance of spatial algorithms. And then when I was writing that up, I moved into an RSE position, all at the same institution. So I've been an RSE now for a little over 6 years, and it was about 2.5 years ago, my former line manager ran off to Scotland and I got a new line manager who kind of gave me that push for, you need to differentiate yourself from your former line manager, you need to build your own profile. So I started thinking about what kind of problems have I seen in a lot of research code, because as an RSE, I work with a lot of code written by researchers and much that they've inherited and so forth. So let's try next thing. So this work has, well, the special interest group part has been supported by the Society of Research Software Engineers. They've, in the past 2 years, kind of built up a system for helping people set up special interest groups. I received a Software Sustainability Institute fellowship in, well, the last cohort, so the end of last year. And also my own institution, they allow me to travel here quite easily because it's easier to spend on my boss's card than to claim the money back from the SSI fellowship funds. So the typical research code author, they're a domain expert. I swear that's supposed to have an emoji. They know a lot about their field, but they're not typically trained programmers. They've not got that formal experience of learning about programming, data structures, algorithms. Maybe they've done an introductory course on Python or C during their undergraduate, but then they've probably had 2 more years before they've gone on to their PhD and their supervisors thrust them. This is the code the person before you is using. You need to use this now or build on top of it for your research. And they don't have a huge amount of time. They're very stressed with actually trying to get the research done, run the experiments, write the papers, and everything else they're trying to pick up during their PhD. And even with PDRAs, they can still be quite short of time. And I've already said, they're often working with inherited code. They might not be familiar with the entire code base. So one of the problems this leads to is just small coding traps. Code that's been used for many, many years, but no one's looked and found these kind of problems. So like a common one here that I've got on the slide, people just iterating lists, trying to handle uniques. They might have a list that's got 100,000, 1 million objects, and they're trying to like find, is this a unique item that I'm trying to add to the list? And they should just be using a set. Like a lot of these, they're engineers, physicists, they know about the mathematical concept of a set, but they've no idea about the data structure. You can replace this in their code, and that particular block of code might run thousands of times faster. And these can be sitting in code for years and lead to what we're calling unreasonable performance. Because these kind of people, the average researcher, they're not running their code on national HPC. Maybe they're running it on local or regional HPC. So they're not having people look at the performance of their code necessarily. They're not going to pop with international HPC. They're not having these checks to get their code on national HPC. They're running it on their local desktop, or maybe they're getting on HPC. There's a lot of researchers who are scared of HPC because they go, oh, it's the command line, that's extra stuff I've got to learn, and they're trying to avoid it. So it's thinking about how can we introduce profiling and performance as something that's accessible to researchers, even if they're not using HPC, although this will affect people using HPC as well. So a case study, a recent project I've been working on, FFEA, so fluctuating finite element analysis. I don't understand anything about finite element analysis. You don't really need to. But what I understand is they have their own code base because they're looking at the thermal fluctuations which cause things to wiggle, which means they can model biological molecules or something. So this is a C++ and OpenMP code base. Development began in 2010. It's had 9 authors in that time. So with those 9 authors, they've been like PhD students. They'll normally be maybe 1 or 2 active authors at a time, but there's not much handover of the code. And these are all PhD students, postdoctoral researchers. And in that time, it's had 12 publications. So this is relatively successful research software. It's not been like a single PhD student and then lost to the darknesses of everything. So I worked on this code about probably 6 months ago for a while, looking at improving its maintainability because it's had this organic growth. So there's a lot of problems in the code base because people have just latched on, I understand this bit, I'm going to add something, but it's in a completely different style to what someone was doing 2 years earlier. And we got out a paper, Better Architecture, Better Research, if you want to read about that, where it's looking at some of the architectural issues. And then they came up with some more money and said, oh, we don't know what to do with you because we've no longer got a postdoc who understands finite element analysis to support you in making these changes. But you know about performance. Can you look at the performance for us? So they've now got a PDRA who is investigating whether this is suitable for their research. So she sent me a couple of her like smaller workloads that I could profile. So we've got this one, which models a bundle of rods, because essentially FFEA has blobs and rods. They're basically two independent things within the code base. So I think that's about 500 rod things that basically just wiggle. And you run it by passing in myofilaments.ffea, which is one of their really complex bespoke file inputs, and that runs in 312 seconds. So we go to profile this, we recompile it with gprof. You'll see like the first 4 lines of that, the dcmake things, they're the standard ways to enable gprof in any C++ file if it's a CMake build project. Bit more complicated if it's a make file or similar, but this is something like we can hopefully get researchers to understand. This C++ is this simple to kind of profile your code. We also disable OpenMP. gprof is just not brilliant for parallel code. There's definitely some spurious stuff that comes in. This particular code base, I did have to make some changes for this to actually build because they had used OpenMP for their just generic benchmarking within the code. So I just replaced that with Chrono. And then to profile it after we've built like that, we just run the code the same as we would before, and then it outputs the gmond.out file, which we pass to gprof. And that will spit us out a text file. So we get these kind of results here, like hopefully some of you at the front can see what we're reading here. So the top line is 54% of the runtime was namespace rod, class rod, method rod, taking input of a const reference to a rod. So that's a copy constructor, 54% of the runtime. Second line, that's 20% of the time, and it's some templatey garbage, which basically means it's a copying of a vector. And then the third line is 12% of the runtime is the destructor of a rod. So like that's highly suspicious. That just looks unreasonable. If you're doing any kind of simulation, why would we be spending 80% of the runtime as that? Just copying the main object of the simulation. Like this is something that we would hope if a PhD student, a postdoctoral researcher gets this profile, they can look at that and go, that's suspicious. I should probably look at this or ask someone who knows what it's about. So start reviewing the code. We look at the rod class. It's got 30 scalars, 28 vectors rather, and 3 strings. So like that's probably where our vector copies are coming from, because we've got a lot of long vectors in this. And it's a big complex class. We're not copying some tiny vector. So then we look down to the methods in this, and every single method, it returns a copy of the rod object. Like, wow. And this is kind of a problem that someone would have hopefully found this, but then we actually look at the implementation. So we've got the comment at the bottom there, which I actually found in the code. It says return star this. So again, this is a pointer, so you're dereferencing the pointer. Return a pointer to the object itself instead of void. This allows for method chaining, except they're returning a copy of the object. So you can't chain that because there's no internal references. They're not doing like pimple or anything. And yeah, so they weren't actually using chaining. It wouldn't have worked. And we can quite easily see what the mistake is here because they've left a comment saying what they were trying to do. So the fix, like check that no one is actually trying to chain these because it wouldn't work and they'd probably have problems. But after you've done that, you can replace all the returns with void and get rid of these copies. Or you could have changed it to a pointer or reference. That would also work, but what's the point if no one's actually doing chaining? So the result of that is the runtime is now 31 seconds in what was about an hour's work. And so if I move on, this mistake was introduced in February 2018. So it's been in the code base about 8 years. And the researcher who first implemented that is long gone. More recently, the PDRA I was working with 6 months ago had used this bit of the code base for their PhD. So they could have had this 10 times speed up in all the work they were doing. What would they have been able to do? More scale or larger simulations, more technical stuff, or even just higher productivity? because this is a wide-ranging thing. It hits all the ROD simulations in the code because every ROD method is making these copies. So the current researcher who gave me this workload, they said, oh, the full simulation, because they gave me a very small one to profile, previously took a week to run. I reran it on HPC now, running in less than 11 hours. So like we can see a big difference here in something that's been sitting in the code for 8 years. Maybe at one time, link time optimization would have fixed it, but with GCC 03, it was not automatically removing that. So this is the kind of unreasonable thing that we're looking at. How widespread are these kinds of issues? We don't currently know. I know from anecdotes, like I've seen a lot of research code with similar issues. Maybe its data structures are wrong. Maybe it's just redundant code. I have friends in industry who also see similar issues. Like I've got a friend who works in an investment bank, they're a quant, their whole team of quants, they're mathematicians, they're not trained software engineers, and they see similar problems coming in. There's an old story from Grand Theft Auto Online, a game that's brought in like 500 billion, or is it million, whatever, where we know they're a game company. They have people who are specialists in performance, but they didn't look at the performance of logging into the Grand Theft Auto Online itself. So someone had implemented their own JSON parser, and they were searching a list where they should have been searching a set. They were not caching, checking the length of strings and stuff like that. And someone who did not have access to the code went and profiled that, solved these, and then submitted a bug saying, please fix this. And they took it on and gave them a small bounty. So there's speculation, this stuff's quite widespread, but we've got no hard research on it. Yeah, so we don't know. That emoji worked. So I'm actually double booked for this at the moment. So a teaching commitment that, well, I'm an RSC which sits within an academic department, the School of Computer Science at University of Sheffield. So I'm able to opt into teaching stuff voluntarily where it suits my agenda. So we have a module in the fourth year computer science where a group of undergraduate students, it can be anywhere from 2 to 6 students, will carry out a research project with the aim of writing a journal paper by the end of the year. So this is like the first frame of the video, which I've left there for them to see, announcing the project for them to apply for, which is, I think it ran about an hour ago, because I think I was booked in at 9:30. So hopefully in a year's time, the students will have put together a coherent data set of looking at this kind of problem at the University of Sheffield. Can we do some very quick, short performance consultations and look for what kind of problems are there? And then what are the demographics of the actual software? Is it mostly new software written by PhD students? Or is it stuff that's all just physics code that's written in C, but everyone using Python is brilliant? We don't know, but hopefully we'll find out. But more widely, how can we enable researchers to catch and address similar problems and these kind of things sooner? So when I first started looking at this 2.5 years ago, I tried to apply for research culture funding at my university. They said it was too narrow, but we were also getting a new HPC system at that time called Stanage. And from that, they managed to fund me about a month's time to develop a short course looking at profiling and optimizing Python. Whenever we do surveys for researchers at the university, Python is the #1 language that researchers are using. I think the most recent one, that was then followed by MATLAB, R, and eventually C afterwards. So developed a carpentry style short course. This took about a month to develop, and it's now in beta status and maintained by myself and Jos Magenda, who is an RSE at KCL. But again, training doesn't scale. It took a month to develop less than a day's worth of training, and we've had a lot more time spent going over and refactoring and improving things with feedback to even get it to a near stable state. But this only covers the most general Python. When we look at what researchers are doing, there's so many niche libraries and small things they're pulling in, where we need to try and get that understanding of a broad approach. It's not just people using one narrow subset of code. I guess there are common things, data structures, NumPy, but there's also a lot of niche libraries where people can make these performance mistakes. So we can't possibly create training for all of these different combinations of languages and libraries. It's just not scalable. Even at Sheffield now, with all the budget cuts, the research IT team who manage a lot of training, they've cut development of trainings, they're developing no new training. They're trying to video a lot more delivery of training, so they don't need to spend so much time on delivering training. And they've also started merging some of the training courses. So like introductory Python, they've merged with introductory R. That makes no sense to me. Like I can use Python, R is a different ballgame entirely. But there's so much like cost cutting. It's very difficult to now develop and like deliver training at scale. So about a year ago, after I started talking about this stuff at RSECon, there was a lot of interest in this. So I started trying to set up a special interest group with the support of the society. And with that, we've got yet another knowledge base. So the goal of this is to kind of build a broad knowledge base of very short and concise introductory guides for different profilers and performance patterns. So like that one I've just shown there, that's kind of don't do redundant copying. Again, like redundant is one of the things, it's probably the most common issue. You profile code and find something redundant that shouldn't be there, but it's difficult to really tie that down to a pattern, whereas we can introduce people to sets versus lists when managing uniques quite easily. And the goal is for these to be quick to write, easy to understand, to hopefully encourage people to contribute to them. Like if you see a kind of, this is horrific, does it exist? No, well, go and add one in. So profilers, you select the language you want to do because there's no point trying to profile with gprof if you're working in Python. And then you can kind of select which type of profiler you want. We need to kind of work on the introductory stuff to get people to this stage. And then we just have sections within these, which are like a quick start for how to profile your code. Most profilers, like MATLAB, it's click run and time. Like it's that simple. Some of these Python stuff, it's make no changes to your code and run it via the profiler or add like one line to your code. Hot path profiling should not be complicated. It is not something where we're asking people, you need to understand program counters and caches. It's telling you this is where time is being spent, and they can look at that and go, is that reasonable? Is that unreasonable? Or do I understand why this is where the time is being spent? Is that where I assume the time is being spent? And if they think not, they can ask someone to like have a look at it for them. And then we have optimizations. This is where we get a bit messy because it's difficult to know how do we separate things and how do we make them easy to discover. Because the goal is if they can profile their own code, can they then find in the optimizations the one that lines up to what they're looking for? Because again, stuff like vectorization, there's a lot of people who don't know about it who are using Python. They might incidentally use it sometimes in NumPy, but they're not trying to get there. List comprehension, it's a lot faster in Python because Python loops are slow. So it's just encouraging people, like if you're profiling your code and it comes up, oh, you've got a really slow loop, what can we do? Can we put it into number? Can we use list comprehension or so forth? And yeah, easy to maintain and expend. It's a Jekyll website. I keep thinking Jenkins for some reason. And it's all written in YAML, which hopefully everyone can understand and make additions to. Like it's all public on GitHub. So I ran a workshop encouraging people to contribute to this at RSECon, and I got about 40 PRs and issues. I'm gradually working through these. I've got about halfway through that, mostly easy stuff, which were mostly complete articles to add to the website. So part of this is hopefully if you're interested in this kind of stuff and want to help kind of build up this knowledge, please get involved. We have a channel on the SOC RSE Slack. We've got a mailing list via the website. It's a Google Groups mailing list. So if you're not got a Google account, just email us and we can add you to it. Tomorrow at 2 p.m. we have the AGM. So again, email me and I will get you a link to that if you're really interested and have the time. And we do have some stickers, although I've not got any more with me at the moment. So I knew I was going to run short, so I brought a second case study because I've got 7 minutes left. So Hybird, this instead of being physics code is civil engineering code. It's got a similar profile. It's C++ and OpenMP code base. It combines a lattice Boltzmann solver with a discrete element model solver. Apparently there's independent highly performant packages that do either of these. But if you look at ones that do both at the same time and interact, there's only like one, which is a very expensive paid bit of software. So development began in 2013 as a PhD project, and now that person is a senior lecturer. And they're still and they're still using this code now with PhD students and postdoctoral research associates, and they've got 23 publications using this software. And they've also got some collaborators. Like it's not properly published software. It's on GitHub, but it's not really hitting a lot of the fair software principles. People have kind of emailed them saying, can I have a copy of your software? This looks useful for my research. So the first profile I did with them, we kind of got this kind of screen of like, yeah. So they've implemented their own vector type. We can see like T-vect, operator plus, operator star, T-quat or quaternion all over this. And this kind of stands out to me straight away as that's probably not inlined. These are all going to be tiny functions. The call overhead's probably quite big. I showed that to the PI and he goes, oh yeah, that makes sense. Like, yeah, there's definitely going to be like a billion calls to vector operator. That's fine. So like there is stuff in profiling that non-technical users have got, oh yeah, that's reasonable. I know that function's being called a lot. But if you understand why that's shown and probably think it shouldn't, you know that we can make changes. So yeah, so 9% runtime is this operator plus, 6% of the runtime is operator times, and they've basically got a massive like bespoke vector file. Nothing, yeah, so nothing's in line. The relative call overhead is probably going to be high because we're calling all of these billions of times. So to fix this, we rename the file to .inl so it's not compiled directly because that saves moving everything into the header. We add inline to all the methods and then we just include it from the bottom of the header. So before the runtime of this thing was 24 minutes. Okay, that's changed to 28 minutes. But anyway, it's a 1.95 speed up. Yeah, I was reproducing this from notes I made 12 months ago and benchmarking everything on HPC. So there's some inconsistencies because I'm trying to write this up as a case study that we can put on that website. So the second profile, LB tutorial. So this is now looking at the lattice-Boltzmann model. So we've got there stood heap select, which again, it's one of these internal C++y things, which is not very nice to look at and difficult to work out. So we kind of control F down the page to find out what's going on. It's called inside LB clean lists. So we look at that code. It sorts two lists. It iterates both the lists to remove duplicate elements rather. And then it fills a new combined list. That sounds like something we can use a set for. But again, I spoke to the PI. That validation code was redundant. So the runtime before was 2 minutes. It's now down to 1 minute. Again, I'm just profiling tutorial things here. They do have stuff which scales up and runs for days. But it had poor scalability, sort of larger scale. We might have seen a much bigger speed up. Third profile on this code, again, more lattice-Boltzmann stuff. 41% of the runtime is inside LB smooth and interface. So it's a large method and I've kind of written some pseudocode here. We've got like 4 layers of iteration, but there's a big comment in there, error, take out from cycle, this is killing performance. So they're obviously aware of this, but they've long since forgotten about it. So yeah, the comment's real. And essentially every fluid neighbor, because it's a lattice-Boltzmann fluid model, it's a discretization of something where there's fluid, gas, and then interface of the cells which sit between. So as cells are becoming fluid or becoming gas, they want to update which cells are in which list because they're managing it as a sparse matrix. So every fluid neighbor of every empty node would iterate the entire list of fluid cells to remove a neighbor if it's present in that list. So like there's a lot of redundant operations here. And again, it's can we use a set? So it's a natural fit for a set, bit more complicated of a fix, but we're essentially deleting that entire awful second loop, adding it to a set, which again, they weren't aware of, but they're a mathematician, they're an engineer, they know the maths. And then just iterate that set, removing stuff later on. And again, that's a 2.87 speed up with something that they had marked as this is slow, but they'd not gone to anyone to say, how can I fix this? They just sat along, well, got on with their research and suffered. Fourth profile. So in one of the profiles, again, I think this one I couldn't actually reproduce on HPC. I think I might have originally profiled this one under WSL, and Windows Subsystem for Linux has some weird performance characteristics. But one thing when we started this project, they came to us and said, our ParaView files are incredibly slow to load. So that they thought we wouldn't be able to fix this. They'd just kind of gone, I don't know why it's happening. It's just got slower and slower. But in one of these profiles, we found that 20% of the runtime was reported of the IO output step method. Like if IO is 20% of your runtime, that's a problem. I think over WSL, it might have actually been higher. Yeah, Yeah, so I rewrote it to use the binary VTK format. That's not an easy fix. Like VTK is a not well documented format, and there was a lot of trial and error in making that work. And we just export whole buffers rather than converting individual doubles with. That's gone weird. Yeah, rather than doing individual O string stream, like they were using the slowest way to do string formatting, and they're outputting potentially millions and millions of doubles. So we got a 25 times speed up to the IO method, but we also sped up ParaView's loading by 40 times because I've not looked at the ParaView code for loading ASCII frames, but it must be horrific. And I think that's it. Yeah, so again, final slide, and that's bang on 25 minutes.
All right. Any questions for Robert? Yes.
So firstly, introduction to Python and R in what? Anyway, no, never mind. But what? Anyway, I'd love to see the course. So my question is, this is so love this, absolutely love it. What I'm thinking, so we're thinking about this at Manchester a lot because we're trying to work out how, you know, how do we get the most out of our hardware, I guess. Have you, so I guess in this situation, you're speaking with individuals, people are coming to you and ask, have you done any analysis or thought about two things? Firstly, what the trade-off is between the overhead of like doing the profiling versus the time you get back or the energy you save. And the second thing is how you might do this as scale as part of a sort of more standard code review process. Is there anything you've learned that would help with that?
I mean, my main concern has always been researcher productivity. Like, there's obviously the benefits of if you're talking to funders, you want to talk about sustainability, they love that. But in terms of actually motivating researchers, it's you can get more research done, you can do bigger stuff. If we just take an hour of your time, or you take an hour of your time, profile the code before you start running your experiments, maybe we can find something, but it's an hour of your time. It could potentially save you weeks of waiting. In terms of how to do this more broadly, I would like to try and move it towards like there's the whole FAIR software, findable, accessible, interoperable. It should really fit into that. Like the basics of reasonable performance should be something that hopefully becomes more standard as when you're trying to publish your code or trying to run your experiments, profile it and see, does this look sane? Because hot path profiling, it's not complex, but I think there's a difficulty where some people, they see HPC and they associate performance with HPC and they go, oh, that's way too technical for me. But profiling or hot path simple profiling doesn't need to be complicated. Or at least it's a lot quicker for them to give us a profile and say, is this reasonable, than for us to sit down with them for 6 hours trying to go back and forth on what have you got that we can profile. So the goal is if we can put these guides here and work with like researchers who are non-technical to improve for them and make the pathway easy. Because some of the feedback from RSEcon was there was a woman who was a recent fellow who'd recently become an RSE, and they're from like the digital humanities background. They looked at that homepage of the website, which is on a past slide, and they go, I don't know where to go from here. Like for me, it's got profilers, optimizations at the top. So that's great. But they were like, no, I need like hand-holding, telling me this is where you start, this is how you make the decisions. So like I've got a long list of stuff to still go through, and we'll hopefully have that kind of sorted by Christmas. But it's just at the moment trying to build and gather the data before we then try and reach research and say, how can we make sure this is accessible for you? And I think we've got a long way to go.
Any other questions?
Thanks for a very interesting talk. I'm not only a chemist, but also part of the EasyBuild community. And as such, we are installing software on quite a wide variety of hardware and hence operating systems. And what we have found sometimes, it's not uncommon, we get told, yeah, it is working on our Ubuntu 2020 installation because all of my users are using Ubuntu 2020. And I think there are two problems here, and one of them you highlighted. It is PhD students, it is MSc students, whoever is available is writing code, leaves, moves on. It is working for me. if I want to have other users to use the code, what you're doing is absolutely paramount, because it doesn't make any sense to have a code which is running 20 times slower on one machine than on another machine, because you're using the wrong compiler, for example.
But again, I think fundamentally some of these things it will be bad on every machine. Like if you're iterating a massive list, trying to check, is this unique? Like it's going to be bad on whatever you run it on. Like these are the unreasonable performance things. And I think something I didn't say is, even computer scientists, people who've done undergraduate computer science degrees, at Sheffield, we're the BCS accredited, British Computing Society. Profiling and performance is not part of the accreditation. I am the only person who teaches an academic module that includes profiling in my department, and that's a 4th year optional module. So we have people who are studying computer science who are not thinking about performance. They may have finished their degree and never profiled code. I can't speak for ACM. They do things differently. They love compilers and that kind of stuff. But at least BCS, performance is not a huge concern. Like there's the data structures and stuff, but people can scrape through that and then not think about profiling code. Because I can make mistakes in programming where I profile and go, straight away, that's terrible, let's fix that. And you just miss things.
I'm shell-shocked to hear that profiling is not part of that degree.
Yeah. Again, I don't set the accreditation. I think cybersecurity is the big one now that's taking a lot of the interest.
Okay, thank you, Robert Chisholm.